Okay, in this video, we're going to look at what is a z-test. And a z-test is essentially testing for the population mean of a normal distribution. So the z-test, the definition is it uses the sample mean to test for the population mean. We can do this if we know the standard deviation and if the population is normally distributed, or we can take at least 30 samples from any distribution using the central limit theorem. What's the central limit theorem again? It's this. The distribution of sample means is normally distributed like this. Now, what does that mean? Okay, let's say I have a distribution. This is a distribution. It's kind of a weird one. All the values are small or big. Now, the central limit theorem states that if I take if I take samples and I mean all those samples, the distribution of means will be normal. So let's analyze that claim intuitively, walk through it for this kind of weird looking distribution. Let's say there's a million points here. They're all small or big. I want to take a sample of 10 data points and mean them. Most of the time, I'll take 5 or 6 from this side and 5 or 6 from this side, or 4, right? But usually it'll be roughly half and half if I'm choosing randomly. And if I choose half from this side and half from this side, the mean is in the middle. So, and that's my most likely scenario. So most of my means are occurring around the middle area. Sometimes, but not often. So not often. Sometimes I'll get 10 data points from here, and my mean will be there. But I won't get it very often. I get most of my data in the middle. Again, sometimes I'll get most from here or all from here. Sometimes, but it's rare. But it's random, so it happens sometimes. But most is in the middle, and we can see that we have created something that looks like normal distribution. Okay, so that's the motivation for the central limit theorem. This is information lifted from an example, a question in the book. And the question is, a machine fills bags of flour with a labeled weight of 1 kilogram. To make sure the bags are being filled correctly, a sample of 40 is taken and their weights are measured. The sample mean is found to be 995. From past experience, it's known the standard deviation is 20 grams. Use the p-value to test whether there is sufficient evidence at the 5% level that the machine is filling bags to less than the correct weight. Uh, this is the data pulled from the question. I forgot, and is 40. 1,000 kilograms. 1 kilogram is 1,000 grams. That's our null hypothesis. We're testing to see if it's lower. We do a test, and this is the sample mean. We knew before this is the standard deviation, this significance level, and the sample space. This number of samples is 40, which means we can use the central limit theorem. So we do, and we want to find the p-value. So less than or equal to 995, and we get our answer as just over 5%. So if the answer is just over 5%, it's not in the critical region, we do not reject our null hypothesis. Now the next question is find the critical region. This is continuous data. Before, with discrete data, like binomial or Poisson, we could approximate and then work out a few examples and see where we're at. But this is continuous data. The data could be 994.9. That's a legitimate data point. But we don't want to do every single point. That would take forever. Fortunately, though, there is a function in the GDC called inverse normal. So we do scratchpad menu, statistics, distributions. Inverse normal is the third option, and it asks you for this information. So area is the area under the graph you want to find, which is 0.05. mu is our null hypothesis. Because again, we assume our null hypothesis is correct. And the standard deviation is 20 over the square root of how many samples we took, which was 40. So we do 20 divided by root 40, and we get our answer for the critical region is 994.8. So anything below 994.8 would have crossed the significance level into the critical region, which makes sense, right? Because 995 was almost in the critical region. A little bit less, it does cross into the critical region. And it's at that point that we reject the null hypothesis. So the critical region is x less than or equal to 994.8. Now I want to introduce a little bit about two-tailed tests. Two-tailed test means we're checking to see if it's in the critical region here or the critical region here. And always in two-tailed tests, our alternative hypothesis will be not equal to. For example, in this question that we just looked at, our alternative hypothesis would be that it's not equal to 1,000. So we have a critical region here, and we also have a critical region here. Now, if our significance level is 5%, that means that 5% of the total area under the graph is critical region. Because the graph is symmetrical, that means it's 2.5% of the area here and 2.5% of the area here. So if we're doing a calculation for a question, we follow the exact same process, but our significance level changes. So if we're going like in our last question, our sample mean was 995. Say it's here. We would not be trying to find if this is lower than 5% anymore. We would be trying to find if it's lower than 2.5%. This is for a two-tailed test. And that in practice is the only difference.